Hey, my name is David Sugar, and here to talk about The Science of Systems, a new book I wrote, all about sustainability, systems thinking, and patterns in nature. This is part of a 12-part video series where I'm going to each chapter. Chapter 4 is all about the history, what kind of systems were developed over time, and how have we come to the scientific theories that we have now across history. So one formula that one could think about history is when have systems of the past transformed to the systems of the present? What were the key changes over time? How has systems of thought developed? This could be frameworks as well as scientific frameworks, different cultural frameworks. So we're going to look at some of these frameworks and how they have changed over time. To give a quick snapshot of some of the key evolutionary points in human history, this is just taking a step back, a really simplified view, but wanted to highlight some of these key changes over time. So from the Paleolithic era, this is more the Stone Age era. The earliest hominoid tools can be found from 3.3 million years ago. This is like axe choppers, different arrowheads, and this shows the use of humanoid tools through stone. The controlled use of fire is expected to have begun about 1.5 million years ago. There's not direct evidence on the exact year, but we see signs going back this far. Around 200,000 years ago, anatomically modern humans developed. A lot of the genetic traits we see in humans were at that time. It's also hypothesized that language and other complex abstract symbolism was kind of developing at this time. 30,000 years ago, we see some of the earliest signs of cave paintings. These showed beautiful renditionings of animals, of also geometric symbols. There's also this notion of a supernatural element that they were describing and drawing things not in nature, right? So a head of one animal to a body of a different animal. And so this shows abstraction, right? Thinking about nature in terms of what's not exactly seen. And this plays a big role in early geometry and there may even be some early pictographic languages with spirals, circles, and other common geometric elements seen in these cave painting sites. The oldest megalithic stone structure, so this is a huge city complex with huge megalithic multi-ton stones, is Göbekli Tepe in Turkey. And this, there's carbon dating going back 11,500 years. And this is one of the earliest signs of, even though the society of the time is hypothesized to be a hunter-gatherer society, they were able to develop this huge city hub. And it's suspected that this was a religious and cultural gathering point. So the agricultural revolution, this is one of the big turning points in human history, at least in the modern understanding of human history, where around 10,000 years ago, societies developed a lot of agricultural societies. These were in a lot of fertile river deltas like Egypt, Mesopotamia, the Tigris and Euphrates River, in India, and China. And these were really represented a change. Instead of hunter and gather societies, nomadic societies, where there could be societies in one place throughout the whole year. They use farming, growing animal, livestock in order to meet their food demands. But this was kind of a different way of living. And this kind of led to large societies, large city states, and more need to organize, also rapid expansion of humanity, because these foods can support large populations. There's also more starch-heavy foods, and our genetic code also evolved to adapt to digest a lot of these foods too, and also milk from other animals, lots of different things like that. And this really led to a large impetus to grow various abstract systems like geometry, engineering, as well as more practical systems like, controlling water, controlling social infrastructure. So some of the earliest signs of geometry used, a lot of this can be seen from the Sumerian culture, other places. The notion of angles. So for example, the Sumerians used a 360-degree angle that we still use today, and different ratios that, if there's a length 1, then something could be length 2. From this time, there was also early approximations of pi, which relates an area to the radius of a circle. And there's also, tablets from Mesopotamia showing Pythagorean triples. So if there's a right angle triangle, for example, 3, 4 on the different sides would make a hypotenuse of 5. And so the Pythagorean theorem in its general form has not been found from this ancient Mesopotamian time, but they've shown that the triples, various solutions to this were known. And this is really important for like engineering a lot of problems that were just common that needed to be solved. So one of the greatest architectural achievements of humanity ever, and also of this time, were the Great Pyramids in Egypt. So just have to do a call out for this. And in order to build these pyramids, extremely precise geometry, architecture, and these are also aligned with astronomy, where the pyramids are due north facing. There's also been various correlations that the pyramids have a similar orientation as the stars Orion. Also, other Egyptian structures align with like the rising of certain stars on the horizon, very precise. So you can see by looking at this architecture, Egyptians knew how to do geometry on a large scale, how to do architecture, moving megalithic stones, and also a really precise understanding of the sky at the time and when certain stars rise where, the true north, not magnetic north. So the rotation of the earth, what axis is that on? And so this is really showing that these ancient cultures had really advanced systems in order to create these structures that we see today. So there's a lot of ancient frameworks used by different cultures in different eras. These were largely from a pre-scientific lens, but were used for natural philosophers to understand patterns in nature and also the patterns of oneself. So this Hygeia pentagram from Greece shows the 4 elements: earth, water, air, and fire or heat, in addition to this 5th element, idea or spirit. And this idea, this pentagram, was used to understand the different phases or different transformations of natural elements, as well as the elements in oneself. And balancing these different kind of internal elements could help lead to health. So the chakra system used in Hindu-related cultures understands different levels. And these correspond to different energy centers. So the root was near the base, near the sacrum, and the crown was near the top of the head. And this also has interesting connections to different layers of modeling the world and different layers of understanding the world, which is deeply connected to systems theory, systems thinking. The tree of life, the notion of some type of cosmic tree connecting the lower worlds and the higher worlds, is a common thread seen in cultures throughout the world, actually. But this gives the idea of nesting hierarchical systems. Science has provided a lot more details about what that means in a physical sense, but this was often used in terms of emotional, psychological, in terms of spiritual meaning and mystical experiences. The Sri Yantra was another one of this stacking. So even though it's pictured as a 2-dimensional shape, it's actually supposed to be a 3-dimensional mountain representing different spiritual levels. So all these frameworks were kind of initial ways to say, how can, people understand life? How can people understand consciousness? How can people understand patterns? And so these were some initial frameworks used through different societies. And there are many more, of course, but just wanted to highlight these. So one of the really interesting ancient frameworks is Taoist cosmology. And the notion of Taoist cosmology is, first, there's this undifferentiated whole known as the Tao. And this doesn't have any separation, so there can be no distinctions within it. The first distinction was the difference between yin and yang. And this could be seen as light or dark, or up, down, cold or hot. And it's basically this polarity that allows definition. There could be further permutations. So once there's 3 permutations of yin and yang, that creates the 8 trigrams. And then these represented 8 different forces in nature. And then taking 2 trigrams together, there's 64 I Ching. And these 64 I Ching elements were used to understand cycles in nature and also cycles of the internal This was often called the external macrocosm and the internal microcosm. And the idea was to understand both patterns externally as well as patterns within oneself. Further permutations of yin and yang, reaches this thing called like the 10,000 things, all the various permutations we see in the world. And an interesting note here is that this follows a 2 to the n kind of mathematical formulation where first there's 1, 2 to the 0, and then 2 to the 1 is 2, 2 to the 3 is 8, like the trigrams, and so forth. So this is also reflected in like logical systems. So how many possible permutations after a true and a false, after 1, 2, or 3, this would have the same kind of structure here. So it's interesting to see this as a kind of very abstract way to understand the world, both internally and externally. And this is interesting framework with also connections to system theory, because in this model, yin or yang is only defined in relation to the other. And so this is a big part about a system, right? In a formal model, one part is defined by its relation to other parts. Like one word in a dictionary is always defined by other words, and those words are always defined by other words. So it's this notion of reciprocal definition in a system. And this was reflected in the Taoist cosmology perspective. So the Axial Age, and this was a critical time of lots of philosophical, religious developments. It's centered around Eurasia, around 2,800 years and 2,300 years ago. There's new religions like Confucianism, Buddhism, Zoroastrianism, Judaism, and there's a lot more trade across cultures, across a wide range. So the Silk Road, for example, was connecting parts of Europe to parts of Asia. And this really promoted cross-cultural exchange, exchanging goods, exchanging ideas. Now, the ancient Greeks during this time had a really uprising of a lot of scientific thinking, of trying to understand nature, a lot of philosophical development. And this is often thought about as some of the roots of Western philosophy. So I'll just call it a few names. There's many more, but Democritus, for example, proposed the idea that nature is composed of these little indivisible atoms, and that different combinations of these atoms make the world we see. And later on, this was found out in atomic physics that this actually had a lot of relevance to our world. We had a lot more definitions through chemistry. I'll just make a note that in quantum theory, there was found to be even a lower level, which has entanglement and all these other things. That's not in atomic physics, but still, this notion of atoms was actually a really useful scientific definition that was proposed at that time. Plato had a lot of different things that he wrote about philosophy, and there's 5 different solids associated to him, the Platonic solids, and these are like the regular solids, like the tetrahedron made with 4 equilateral triangles, the cube made with 6 squares. There's the octahedron made with 8 triangles, the dodecahedron made with pentagons, icosahedron made with 20 triangles. And he correlated each of these elements, these geometric elements, with phases or elements in nature. So fire, earth, water, air, and even space and time, the aether. So this correlates with that pentagram we saw earlier. And now with modern science, we know that a lot of these geometries are actually related to molecular geometry, also related to crystal geometry. There's a lot more definitions about what geometries applies to where. But the key part here is that Plato and others were really thinking about how does geometry play a role in natural patterns. And while the scientific methodologies at that time were fairly rudimentary compared to what we have now, there's actually some strands of truth in there, right? That there is geometry. It's a little more complex, it's a little more different than these 5 solids, but this is some of the initial groundwork was laid. Aristotle was another one of Plato's colleagues and kind of successor in a lot of ways. And he developed a lot of this syllogistic logic. So, if A is B, and B is C, then it should be the case that A is C. And this really laid the groundwork for like modern logic and modern philosophy. Euclid is known for doing a lot of geometry He wrote the book Euclid Elements, and in there it laid various postulates for geometry and all these proofs that can be found through these initial axioms. So this is taking an axiomatic approach, seeing what proofs can be made, and this really led the foundation for Western science. So wanted to highlight that after this kind of axial age, going into the medieval age, there was a whole bunch of these large empires that came about. Some of them we talked about the Greece. So they built huge temples like the Parthenon in Athens. The Roman Empire, right, is a huge expanse of land that they controlled. They worked on large engineering, large aqueducts, and the Pantheon in Rome, right, is this huge dome concrete structure still standing today, the largest unreinforced concrete dome ever built and still today. They didn't use steel at that time, it was just pure concrete. But Roman concrete was a huge advance where you don't have to chop up stones to fit exactly, you could actually pour concrete and make a stone. So the Islamic empires growing from the Islamic states near the medieval was a huge new empire. This was after really the fall of Rome, more into the medieval era. And there was great advances where the Islamic scholars at the time, they took like Euclid's Elements, for example, that was lost during European Dark Ages. They translated that, they built upon it, they developed algebra, they use a positional based system like we do now, where the numbers represent a digit, but also the power of 10. Decimal point notation. This was drawing from Hindu sources, but they use these sources. So they advance mathematics, they advance medicine, they advance engineering. They also have these extremely intricate geometric elements that they use associated with their religion. And this was seen a lot in their mosques. So going into the European Renaissance was another huge change in history. This was kind of led after the European Dark Ages. A lot of those advances from the Islamic empires were transitioned over. So Euclid's Elements was reintroduced into Europe. And this promoted this neoclassical view in Europe where they were praising these old ancient cultures like Greeks and Romans, but building upon them, trying to do more. So you can see a lot of the architecture at this time was reminiscent of Greek, reminiscent of Roman, but bigger and different. New methods to create domes, new science. And the Vitruvian Man by Leonardo da Vinci, is one of these great drawings during this time. Leonardo was a polymath doing lots of different subjects. And this really shows a combination of art, anatomy, but also you see here there's a square and a circle. And this is actually trying to solve an ancient geometric problem, which is to say, when does a circle have the same area as a square? And it turns out that this can't actually be formally proven with geometric elements alone. You need like computational, you need other approximations to get this exact result, but this is one of these approximations. So this symbol, Leonardo, it has a lot in here, right? It's about art, and it's also paying homage to the classical geometric problem and trying to solve this. So one of the big developments after the European Renaissance was Newtonian physics. And this was one of the foundational building blocks to the Western scientific approach. And this was a dramatic change from Aristotelian way of underthinking about the world. In Aristotelian perspective, objects have various causes. They have like intrinsic cause. So something, falls because it has a cause it wants to fall. A leaf grows because it has a cause it has a desire almost. And this is thought about in teleological ways. So nature was understood through a teleological perspective. However, through Newtonian physics, it's all about understanding the world through forces. So there's not this like mind and this, various matter or whatever that it has a desire, has a cause to do this or that. It's really understanding the world in terms of forces. So basically, Newton posed these three rules of kind of classical physics, which is that an object's motion does not change unless acted upon by a force. So there must be a force to change an object. And that this force equals the mass times acceleration. So more force for a given mass would mean more acceleration over time. Also, every force has an equal and opposite force. So if I'm standing on the Earth's grabbing, pulling me down, but my feet are pushing up against the Earth and holding me up. Because if the forces were not equal and opposite, then I would be moving, right? If there's basically the acceleration until there's a force to counter that acceleration. So this provides a way to understand movement of objects, and not only on Earth, right? So how does a trajectory of a ball move, but also objects in space. And so this is really saying that Newton was saying the same laws apply to the astronomy, to the world that we see in the stars, to the objects we see on the planet. A lot of like Aristotelian physics and stuff, they had various spheres, and it was kind of, okay, there's an earthly domain, and then the stars are kind of this fixed stars, and they rotate and stuff. But the rules weren't the same, right? The rules were often very different. Newtonian physics is saying, okay, let's look at the universe as a whole. What are the rules that are symmetrical to everything? The same rules of physics should apply across everywhere. So one of the key abilities of Newtonian physics was to describe orbits of planets. So, for example, the moon's orbit around the Earth. And a key point here is that the moon has a force of gravity to the Earth that's pulling it down, but it's moving at a velocity, so it never hits it. Every time it tries to go down, it curves more and it goes around. So that same force of gravity is, the apple falling from the tree. So basically the same forces of gravity on Earth are also in the stars. It's the same forces everywhere. And this solved, a big, outstanding question, even posed since the time of Plato, which was to try to understand the movement of the celestial bodies through a geometric theory. And Newton basically did this. Now, I would say Johannes Kepler had discovered that planets move in orbits, and various rules around how much area is traced out in a given time will be equal, and other kind of relations that are followed. But this enabled to help predict a little bit about planets, but it was kind of unclear why these rules apply. So in Newton's rule, right, if the force of gravity is inversely proportional to the distance squared and the masses of the objects, plugging that in now gives you the results of Kepler. That basically planets must move in ellipses, that they would trace the same area in equal time intervals, and all the other relations that Kepler found. So basically Newton provided this mathematical theory to align with all the evidence, all the observable evidence about how celestial bodies were moving at that time. It's not perfect. We now use relativity, general relativity, to have more precise formulation of gravity. But this was revolutionary, and it provided a means to really calculate forces, trajectories in a precise way. And this uses calculus, was a new way of understanding like infinitesimal changes over time, and that helps understand force acceleration. Another thing that Newtonian physics can be used for is, for example, like if different billiard balls are smashing. So if you have a pass or initial state, the velocities, the masses, the directions, now you can calculate where it will be in the future. And a big part of this is that for every force, there's an equal and opposite force. Well, that is basically the conservation of energy. It's kind of stated in different terms. Energy wasn't, as it's known today, wasn't really thought about back then. But still, you could calculate a lot of these things. It really led the foundational, framework for physics. And this was a really big turn in science, right? It really provided a way to say, this abstract geometry, this abstract mathematics, there is a very clear way that we can calculate trajectories of planets. We can know ellipses, we can know when certain astronomical events will happen. So this provides a mathematical theory to understand the patterns of nature. So now, wanted to give a snapshot of some of the, after the European Renaissance, after this modern science. Now, some of the new things that happened was that trade society began to grow and grow and grow. And one of these big changes was the Industrial Revolution, kind of in the 18th, 19th, 20th century, where more and more modern technologies were used, like printing press, fossil fuels, kind of like railways. And this really led to expanse of commerce, being able to go across the whole world. And the 20th century saw a lot more economic expansion, a lot more growth, a huge population growth. So a lot of this was fueled by, Newtonian physics in a way, right? Because now there's a mechanistic way to understand the world. More science was being developed, like thermodynamics. And now science was being used in terms of engineering, in terms of building solutions, in terms of, growing society. But there was also negative, ecological and also social ramifications of this, where I'll just start socially, a lot of these various colonial empires controlling huge swatches of land. And now this is causing a lot of the social injustice we even still see today. A lot of that was caused by, extracting resources and not disrespecting various social classes. And, this is often seen from a lot of European empires during this time, controlling huge areas of land. And that really, caused a lot of social injustices that we see today. Additionally, in terms of ecology, the amount of carbon dioxide rapidly increased to the 21st century, and also the extraction of other natural resources. So now society, we have all these tools, all these technologies, all these different countries have grown. But now the same tools that help society grows may also lead to their demise, right? Where these technologies are extracting natural resources, and now we're facing climate change and other global crises. And now it's like another revolution in science in the 21st century, where now sustainability is part of science. In Newtonian physics, sustainability was rarely considered, right? You're just considering how these little atomic particles move, or planets. The humans were often seen kind of almost as separate. But from a sustainability point of view, humans are part of the earth. And now we can quantify it mathematically. We can show that, human extraction of resources, human emissions of carbon and other carbon dioxide and other gases can actually influence the entire global atmosphere, can influence the global weather patterns. So now, because humans are such a large part of the world, we're actually integrated into the science, right? It's not just about studying the world as the world. Now, in order to understand what the world is doing, you have to understand humans too, because humans can interact at a global scale and change the world. So sustainability science is all about saying, now that we understand nature of humans connected with the global system, how can we design a sustainable future? So thanks for tuning in. This was video 3. If you want a free PDF of the book, you can go to davidsugar.com/book, and I'm offering a free PDF. Additionally, if you want the paperback, you can go to Amazon, get the paperback, seen in person. There's also a link on my website. Thanks for tuning in, and stay attuned for new system science lectures. Thank you.